Picking up where we left off the last time, we're going to continue to do some calculations involving a weak acid, strong base titration. In particular, we were focused on the compound CH3COOH, which is acetic acid, and titrating this compound with NaOH, a strong base. The data is the same as in the last video, and we're actually going to pick up where we left off. We're going to consider what happens when we add 75 milliliters of NaOH to 50 milliliters of 0.1 molar acetic acid. So if you recall, we have dispensed with A and B. Feel free to go back and review those if you need to. When we hit this calculation for C, we're actually going to consider what happens when all the weak acid is gone and how our pH will be dependent on excess base. This is what's going to give us our pOH and then consequently our pH. The other thing that we're going to look at, we're going to actually move backwards, if you will, because I also want to address something called the midpoint of a titration. This is another important stage. Some ways I saved the best for last, because when you actually calculate the midpoint of a titration, you can use the Henderson-Hasselbalch equation, which I'm going to just abbreviate to HH equation. Super handy equation to use for this type of calculation, will make your life extremely easy. So stay tuned for the midpoint. I'll be explaining all of this once again in some detail. After the equivalence, this is when, as already pointed out, weak acid has been consumed. It has been neutralized by strong base. That means the addition of any more strong base is going to dictate pH, because the solution has become increasingly basic very rapidly, and we can take the negative log of the OH concentration in order to ultimately get a pH. However, we want to know, how do we get at this excess base? How do we figure this out? Well, not surprisingly, this is going to be thanks to our ice chart. So we're going to use the ice chart to get at the molarity of our excess base. We're going to calculate pH from that OH minus concentration. Notice over here in this figure, we have the equivalence point here. We go up super rapidly after that, and then eventually things start to level off. That's because as we continue to add more and more base along this line, the solution is so saturated with base at this point that it isn't really making much of a difference to the pH, where it's basically starting to level off at this point. Something to consider. At this point, we are now going to calculate the after the equivalence. I always feel like saying after the flood of NaOH. So what does that mean? It means we've added 75 ml of our NaOH. And this is well in excess of our 50 ml of 0.1 molar. So clearly all the acetic acid is going to get consumed by this amount of NaOH, and we're going to have leftover NaOH. I say clearly, I will actually proceed to prove it to you. Super quickly, 0.05 ml times 0.1 mole per liter. This is our CH3COOH, is going to give us 0.005 mole of acetic acid. And then we have 0.075 ml of our 0.1 mole per liter NaOH. So that's going to give us 0.0075 mole of NaOH. We're going to put these numbers in here, 0.005, 0.0075, 0 here, 0 here. Water is going to develop a complex because I'm ignoring it again. Now, notice here, these things react in a 1-to-1 ratio, right? takes 1 mole of NaOH to react with 1 mole of CH3COOH. That means we have more NaOH than we need, and the only amount of NaOH that's going to be used up is the amount of CH3COOH it has to react with. So we're going to take away 0.005 on both sides here. Notice we're going to end up with 0 moles of NaOH of acetic acid, and we're going to end up with 0.0025 mole of NaOH. This is in excess. We're also going to have some acetate ion because that gets formed in this whole process. We're going to have 0.005 mole of acetate ion. What we need to focus on here is our NaOH. This is the compound that's going to dictate the pH. However, we must be careful that we switch at this point from moles to molarity. What's the total volume of our solution? Well, we started with 50 ml. We added 75 ml. Looks suspiciously like it adds up to 125 ml, which is 0.125 liters. Now, since we have at this point in excess 0.0025 mole of NaOH, we need to take the negative log of that. So, you know what? I'm going to let you do the heavy lifting here. This is going to give us the concentration of OH minus. Once you have the concentration of OH minus here from the excess NaOH, as just pointed out, this will give you what? I'm having fun here. POH, going around in a circle. From POH, we can get pH. And you're done. Once you have pH, you have solved the problem. Now I'm going to predict, not prove, because I'm making you do the work, that at this point we're going to be probably somewhere in this point of the graph up here. So in other words, we're going to have pretty high pH at this point. So do the calculation. Prove to yourself that upon the addition of 75 ml NaOH, we have a quite basic pH. We have neutralized all our acetic acid. We have excess hydroxide ion in solution. It must be basic. Just a quick note. You may be asking yourself, why did I ignore this CH3COO minus acetate ion? It is true it will hydrolyze water, as we have seen before. But there's not very much of it, and the fact of the matter is whatever it generates in terms of hydroxide ion is going to have a very minimal impact on the pH relative to the excess NaOH. So happily, we can just ignore this hydrolysis reaction, although it's probably a good idea if you recognize that it's still taking place. Let's proceed to the in-between of the before and the at, aka the midpoint. I'm going to first show you what I mean by the before and the at. Well, the before was before we added any strong base, right? And the at, as we know, is the equivalence point up here. Notice that the midpoint falls right in between these two things. I will define it quantitatively in a moment, but the first thing I want you to do is notice that the midpoint is in a very interesting part of the graph, because notice that on either side of the midpoint, the pH is not going up rapidly at all. It is a fairly minimal change in pH. However, once we get past that certain distance on either side of the midpoint, pH goes up very rapidly, as noted before. So this is an extremely useful and informative area of the graph, and I'm going to explain how you can use Henderson-Hasselbalch equation to calculate pH when you are considering this portion of the graph. So we want to know pH in between the beginning of the titration and the equivalence point. This includes this midpoint, sometimes referred to as the half equivalence point. What does it mean quantitatively? It means that we have consumed exactly half of the initial concentration of our weak acid. In turn, that means we're going to have exactly half of its conjugate base. Think about the equation, that will make sense. This happens when we have added enough strong base to react with exactly half the initial concentration of weak acid, in turn forming an equal amount of conjugate base. So you can think of this as equimolar or equal moles of weak acid and weak base existing simultaneously in solution. Pretty cool. It is used to define this buffering range, as noted. As a reminder, this is what the Henderson-Hasselbalch equation is. We can set pH equal to pKa, that is the negative log of the acid dissociation constant, and then we add to that number the log of the conjugate base concentration over the conjugate acid concentration. So this sets us up to continue on to the actual calculation itself. Away we go. As always, we're starting from 50 ml of our acetic acid, and note that this time we're adding 25 ml of NaOH to get to the midpoint. Why is that? Well, if we think about it for a moment, 50 ml of 0.1 molar acetic acid is going to give us 0.005 mole of acetic acid. 25 ml of 0.1 molar NaOH is going to give us 0.0025 mole of NaOH. That looks suspiciously like half the amount of CH3COOH, so that will consume half of it, form an equimolar quantity of acetate ion. Let me show you how this looks in the ice chart. 0.005 here, 0.0025 here. All of this gets consumed. Left with 0 here, 0.0025 here. Half of this is remaining. Oops, left out a 0. Start from 0 over here, plus 0.0025 here, 0.0025. Keep in mind this is mole, right? Now, technically we could, as before, we could say, okay, the total amount that we have here, 50 plus 25 is 125 ml, which is 0.125 liter. If we wanted to work in molarity, we could, but we actually don't have to. And I'll let you in on this secret, ignoring H2O once again. So pH equals pKa plus the log of base over acid. Doesn't really matter here if we take 0.0025 over 0.125 or just 0.0025. This is going to cancel out to be 1. We have equimolar or equal mole quantities of CH3COOH and its conjugate base. So no matter what, it's going to be equal to 1. And this is going to reduce to the log of 1, which equals 0. That means our pH is simply equal to pKa. Isn't that a beautiful thing? pKa, in turn, is the negative log of 1.8 times 10 to the negative 5, our Ka. And in my omniscience, in my great wisdom, I happen to know off the top of my head that the negative log of this number is 4.72. At least I hope I've gotten that right. And that's it. You've done it. Keep in mind that this Henderson-Hasselbalch equation can be used as long as you have a relative concentration of acid and base. So in other words, whenever you're solving a titration problem, if you have some base and some acid, you can use Henderson-Hasselbalch. You cannot use it before the titration has started. You cannot use it at the equivalence point, and you cannot use it after the equivalence point because you don't have these relative concentrations. Anywhere else in your titration is fair game. On that note, as Bugs Bunny would say, that's all, folks. Until we meet again.